Okay, hi guys. We want to do circuits. In circuits for electricity science 3, here's what you need to know. So we have a series circuit. In a series circuit, you have you have resistors which are connected to one winding. So we can say this is resistance 1, resistance 2. They are also connected to a battery which has 2 cells which are connected in series. So things which you are interested in is to see the flow of current related to the 2 cells, is for you to know that each cell has an internal resistance. It will be represented by small r for each cell and an EMF for each cell as well. So you are interested in finding the total resistance, of which the 2 resistors typically you will concentrate in. There's the external resistance, which does not include the one in the battery. So typically you will add your resistance for R1 plus R2 when they are connected in series for the total external resistance. Then you have your internal resistance. Internally, it is inside the battery. This battery which has 2 cells. So to do that, you will then add these two. Now for the battery, typically our resistance is the same for each cell. So in this case, you have an option of saying for your internal resistance, it's either you will say R plus R, which in our case will give us 2R. Alternatively, you may say the number of cells times each internal resistance. So that is an alternative method on how to represent your internal resistance. So then from there, when you look for the total resistance of the whole circuit, you are very much adding your external resistance plus your internal total resistance. So resistance wise, this is what you guys should be interested in. Additionally, you may need to find your EMF. EMF for this circuit here, in this case, you have 2 EMFs in each cell. So typically we say voltage in a series circuit would add. So EMF, part of your first options for finding it is to deal with these 2 EMFs here because they're in series. Similar to how you found your internal resistance here, you would say E total equals to your E, the first EMF plus the second EMF. Thus you have 2 EMFs. Alternatively as well, you may say number of cells times each EMF. Your other option then is to say total EMF is equals to your terminal voltage or potential difference plus your total current passing through the internal resistance. So this is the alternative formula for finding total EMF in this circuit here. You're saying your terminal voltage or potential difference across the circuit plus I total times RT internal resistance. The main thing typically they may need you to calculate is your total current. So for our total current, then we will say it is our E total divided by the total resistance. So you will then see that from time to time they may simplify a couple of things in this formula, such as having to substitute your formula for E total as N times E over, even the one for R total, they may write it as R external resistance plus R. Additionally, for your potential voltage, your potential difference, typically it's either the simplest way of finding your terminal voltage is to just say your total current times the external resistance. Alternatively, you do have the option of making it the subject from this formula here. So if that's the case, then you would say V equals to E total, you take this part to the other side, minus I total times R internal resistance. So these are the formulas which you need to know. We'll write the symbols at the far end because they're similar with the ones for parallel. So for parallel, in a parallel circuit, this case I have two resistors and they're connected in parallel. Typically in parallel, we will tell you that current divides. Maybe before I go into parallel, let's go back to series. So there's a couple of things which you may need to know. We have the concept or principle of voltage drop. When this current passes through this resistance, there's a form of a voltage drop. So they may ask you calculate the voltage drop through resistance number 1 or resistance number 2. The voltage drop through these two resistors may be expressed as, so the voltage for the first resistor, resistance number 1, can also be expressed as I total times the resistance it's passing through, same as the one for R2. It may be also expressed as V2 equals to I total times R2. So that's E total as well. In a case where you don't have your values for your battery for each cell, the alternative method for finding E total is to just add the voltage drops throughout that whole circuit there. In this case, it would be V1 plus V2. Additionally, current in a series circuit is the same. The same current which should pass through R1 may be expressed as I1 is the same current which will pass through R2, I2. So thus, if current is the same, then I total is the same as I1. It's also the same as I2. So these are standard formulas, all of these here. It will just depend on the question you are doing. Let's go back to the parallel circuit. So for parallel circuit here, we then say current in a parallel circuit is not the same. We will then say it separates, it divides. So the current which will pass through R1, we may express it as I1. The one passing through R2 is I2. The one coming from the supply is our I total. So then to find total resistance without the internal resistance, our R, in this case, you have a couple of options. Part of your first options are to use the standard formula, which would be expressed as 1 over R equals to 1 over R1 plus 1 over R2. The intention is to make R the subject of the formula. Now it turns out sometimes most people find it difficult to make R the subject of the formula. They happen to maybe write the final answer and struggle with just the final answer for the second side, for this side, and struggle to make R the subject. So alternatively, all you can do is you can just say R, then everything this side to the power minus 1. And this should make your life easy in a case where you have two resistors connected in parallel and you just want that resistance which is connected in parallel. For the battery here, I've represented it as though it's still connected in series. But there's a case where they may happen to give you a battery connected in parallel. Now, this is not, they hardly do happen to give us a battery connected in parallel, but it may happen. So in this case, my number of cells, I have 3 cells, 1, 2, and 3. Each cell has an internal resistance and also has an EMF. So in this case, for my internal total resistance, we will disregard this one and refer to this one. Remember, each internal resistance is the same, each EMF is the same. So in reference to this specific battery, if I wanted to make my total internal resistance the same, based on this one, if I were to use the same formula I was using earlier on, it would be 1 over R total equals to 1 over R plus 1 over R plus 1 over R. So according to maths, it says if the denominators are the same and the fractions are adding, you may add the numerators. So in this case, I have R total equals to 1 plus 1 plus 1 over R, whereby I can still express this as 3 over R. The intention is to make small r total the subject of the formula, so I may apply an inverse both sides just to make my small r total the subject. In order for us to do that, we will have RT equals to R over 3. So this is the alternative method for finding R total. It can be simplified quickly by saying, if you to look at the last formula I have here, you will then notice to find my R total, I divide my total resistance by the number of cells I have. I had 3 cells, thus I've divided it by 3. Yes, the manipulation technically proved it for us down here. So the alternative way of going through all of this is to just say R total equals to internal resistance divided by number of cells. So that's how you would go about it for this specific battery, not that one. We have to still find our R total, same principle. You're still seeing your external resistance plus the internal resistance in the battery. You're still required to find your EMF. Now EMF for a parallel circuit, for this one here, a battery which has cells connected in parallel like this, for your E total, EMF is the same. So if you're to label this as E1, E2, E3, then you'd be covered. So you'd know this would be E1, it would be the same as E2, it would be the same as E3. So total EMF in a cell is the same EMF in a cell, or I mean in a battery which has cells connected in parallel, is the same. Next, you still need to find your current. For current, you're using a similar formula from the previous. Before we go there, the alternative formula for E total then would still be the same as the previous one. The terminal voltage plus I total times the total internal resistance. For I total also is going to be then E total over R total. Now, I forgot to mention, oh, I did mention, fortunately, that terminal voltage would be your total current times the total external resistance. So even in this circuit here, we're still saying terminal voltage is still I total times the external resistance total resistance. So yeah, these are our formulas. They may still simplify this. Fortunately for this one, because it's a parallel one, you already know E total is the same as small e over total resistance would be expressed as R plus small r, but you don't need to go through this. You can just find your E total and your R total. Also, current in a parallel circuit, typically we say it adds. If you're to check this I total here, it reaches this point. As soon as it reaches this point, some current moves up, the other one moves towards R2. So I total can then be expressed as I total equals to the addition, because what happens is I1 passes through this resistance, it still comes back at this junction, your I2 still comes back there, they still come back and add back to I total. So you have I1 plus I2 in a parallel circuit. So this is the alternative formula for your I total. What else? So power. Then we have formulas for power. Formulas for power, they may require you to calculate power dissipated across any of these resistors, whether connected in series or parallel. So to find your power formulas for power, we have current times voltage, we have power, we have I squared R, we have V squared over R. I think these are the standard formulas you would have to use in case they would require you to find power. So these are our equations, and we need to make sure we know how to use them. So we are about to start to do an example and see how it goes. Alright, so in this question here, it says an open circuit EMF of a certain cell was measured and found to be 1,48 volts. This refers to an EMF for one cell, 1,48 volts. It says when a resistance, a 2 ohm resistance, was connected across the terminals, a current flow of 0,6 amps was measured. So we are given this resistance of 2 ohms was connected across the terminals, a current flow of 0,6. This current was measured amps. You read the first question, it says calculate the following: calculate the internal resistance of the cell. The second question says calculate the terminal voltage with the 2 ohm resistance connected. So this is the given information we have. We are told to find this information here. So for internal resistance, all of this is happening within or around one cell. We have a cell which has an EMF of 1,48 volts. Then we have a resistance of 2 ohms, and when this 2 ohms inserted across the terminal, the current passing through is 0,6 amps. So to work with just this information here, question says calculate the internal resistance of the cell. With this case, to refer to our formulas, if there's any formula which would be more relevant, is this one for EMF. In this case, as we're looking for 1.1, it says 1.1. I'll use small letters considering that we're working within a cell. You can still use the capital letters. So we're saying E equals to our terminal voltage V plus I total, or let me just express it as the current passing through the resistance times the resistance, which helps us to find this current here. So in such a case as this one, we do have our EMF, we have a current. In fact, I did not write this formula correctly. We are looking for the internal resistance. According to this formula up here, it says EMF equals to voltage, terminal voltage plus our I total times the internal resistance. So there. So in this case here, we have this. We might need to find this, and we are given that we are looking for the internal resistance. So for your terminal voltage on the side, to which the next question they need to find, terminal voltage, we know it as the current times the external resistance. So in this case, you can represent this formula into your equation here, whereby you may write it as E equals to our IR plus our internal resistance. So in this case, then it's going to make things a bit easier for us. So you go about it, you say 1,4 equals to our current. We are given 0,6 times 2 plus 0,6 times our internal resistance. You will simplify certain values. You have 1,4 equals to 0,6. Let's see, 0,6 times 2. We have 1,2. 1,2 plus 0,6. You take 1,2 to the other side, you'll have 1,4 minus 1,2, 0,2, 0,2 equals to 0,6 R. Divide both sides by your 0,6. Then our R, we have 0,2 divided by 0,6. 0,2 divided by 0,6. And we have 0,333. 0,333 ohms. And so that's how you would go about this one. 1.2. So this is your internal resistance for the cell. In here we have 0,333 ohms, just around there. So the terminal voltage with the 2 ohm resistor connected. Terminal voltage, we've covered it this side. We've already expressed our formula. So also we actually managed to find it here, but you can just go about the calculation again. V equals to current times our resistance. This is the 2 ohms, so it's going to be 0,6 times 2. We got 1,2 volts here. And you're done with this question. So this is not so much of a standard, but they've asked it before at the final exam. Let's see if we can come about and do another question again. So for this one, it reads as follows. It says 3 cells, so we have number of cells, 3, each with an EMF. We have 4 volts, of 4 volt, and an internal resistance, small r, 0,1 ohm per cell, are connected in series. So we are told this is in series that's in series. Not only that, but they still showed us here. So we have each EMF here and the resistance that are connected in series in the figure shown below, or in figure 1. So here's our figure here. Then they've already given us all other data in our circuit here. So in this case, they've sketched for us the circuit, and it's our responsibility to try and see if we can interpret it correctly and apply the calculation correctly. So first question says calculate the resistance of the circuit, the total resistance of the circuit. So for the total resistance of the circuit, we have these two that are connected in parallel, connected to an ammeter here which has a resistance 0,2, an armature with a resistance of 0,2, but this is a symbol for an ammeter, which is its main purpose is to calculate current readings. So we have another, from this one here, we have another resistance connected in series, which has a voltmeter here, and then we have this resistance. So fortunately, some of our resistors are already labeled. We have R1 and R2. This one we can say RA, R3. This one is supposed to be R4. So let's go through our calculation. 2.1. So for 2.1, what we can do is we can just break it to small pieces. We first find your parallel resistance. From there, you can add it to the ones which are connected in series. Also, you can also find your total internal resistance as well. So to do that, you can maybe say R parallel, and you deal with the parallel resistors. So here we have 1 over R1 plus 1 over R2 to the power minus 1. And let's go. So here we will have 1 over 2 plus 1 over 3 to the power minus 1. And it gives us 1,2. 1,2 ohms. From here, you may find the total external resistance. To find the total external resistance, you will add all these other resistors. So to add them, it's going to be Rp plus your Ra, which is this one. This is our Ra. Oh, they labeled it as R4. It's supposed to be Ra, then that would be R4, but that's okay. Plus R3 plus R4. So we will have 1,2 plus 0,2 plus 1. It's this one plus the 0,8, 0,8. We have 1,2 plus 0,2 plus 1 plus 0,8. We have 3,2. 3,2 ohms. Internal resistance is saying number of cells times each resistance. So we have 3 cells times each resistance, which is 0,1. So here we have 3 times 0,1. We have 0,3 ohms. So to find our total resistance, you're just saying 3,2 plus 0, well, let's start with the formula first. R plus R total, which is 3 comma 2 plus 0 comma 3. It's going to give us 3 comma 5 ohms. So someone will say maybe these steps are very exhaustive, they're too long. The alternative formula is literally just substituting everything into the formula for R total. So if you're to do that, then you would very much be substituting all the steps which I just represented at the top. So to do that, someone else would look at the circuit and have such a representation. So seeing that these two are in parallel, let's say 1 over 2 plus 1 over 3 to the power minus 1 plus this resistance of 0 comma 2 plus the 1 ohm resistance plus 0 comma 8 plus our internal resistance at the end, which is 3 cells times each internal resistance, and they would still get the same answer, 3,5 ohms. With this method, typically when they mark you for the parallel circuit, for adding all these resistors, well, these ones which are in series, and then for that one and that one. So it's typically around 3 marks or 4 marks. So the danger with this one is just making a mistake if you're to use the last method here. So that's why with this one we break down our steps. That's the whole idea. We break down our steps. So yeah, let's go through the next question. 2.2 then says calculate the ammeter reading. The ammeter reading, in this case, the current reading. So for our current, we may use the formula E total over total resistance. On the side, we may find our E total. Remember, our cells are connected in series for this battery here. So E total, each EMF in our case has 4 volts. So you may then see N times E equals to 4. Well, we have 3 cells, so it's going to be 3 times 4 will get a 12. You say 12 divided by 3 comma 5, and then let's see, we have 12 divided by 3 comma 5, 3,429, 3,429 amps, and you're done with this. Next question, 2.3, the voltage across A and B, the voltage drop between these 2 points, this B is supposed to be around there. So it's the voltage passing through the 1 ohm resistance. So all we're going to say is, considering we know that current in a series circuit is the same, we are interested in just finding the current which will pass through this resistance times the resistance it's passing through. So the voltage through the 1 ohm resistance is total current times the 1 ohm resistance. This resistance was R3. So labeling wise, it's not a challenge. It's very much up to you. There's no standard for labeling. Someone else will say, considering that it's passing through resistance number 3, maybe this is still VR. I wrote it as V1 ohm. Even this V3, it's important. If there's anything, I mean, it's an alternative method, not necessarily that it's important. So I was saying, if there's anything that you're interested in is you applying these correctly. So we have a resistance of 3,429 times 1, and you'll get 3,429 volts. Last question says, the current through the 2 ohm resistance. Our 2 ohm resistance is in this parallel circuit here. It's in there. So then we say voltage in a series circuit is not the same. Voltage in a series circuit is not the same. You need to find, but in a parallel circuit, it's the same. So you may want to find the voltage drop across the parallel circuit. As soon as you found that voltage drop, you divide it by this 2 ohm resistance. In a case where you find yourself using the EMF to find the 2 ohm resistance by dividing the EMF by 2, you will get the calculation wrong. So for our voltage drop across that circuit 2.4, you're going to say voltage equals to current, total current times the resistance in the parallel circuit. So we may also say this is V parallel as well. So the resistance we got was 1,2. So it's going to be our current 3,429 times 1,2. 3,429 times 1,2. 4,115. 4,115 volts. Then you can find your current for the 2 ohm resistance. That it's R1. So I can label this as I1. This is going to be V parallel divided by R1. Then you'll have 4,115 over 2 and 4,115 divided by 2. We have 2,058. 2,058 amps, and that's how you would have to go about your calculation. So these circuits are quite friendly. There are interesting questions out there. Your purpose is to just know how to go about your calculation. Maybe later on I might do more examples. So yeah, all the best.